Hello. The microphone. Can people in Zoom hear me? Pardon? Oh, sorry, I'm not very good at computers. Huh? Oh, you're so smart. Okay, can the people in the Zoom hear me? Clear? Cool. Right, so we are at 2 o'clock, so let's get started. So hopefully you can hear me, and the announcement I want to make is that tutorials will start next week. I think the more practice you have, the better. So tutorials will start next week, which is week 2. So I've already posted tutorial 1. I've already posted tutorial 1. So you can attempt it, and you should attempt it. And the tutor will go through the questions. I've already typed the solutions. So yeah, after the tutorial, after the Thursday tutorial, we will post the solutions. Okay. So you should attempt it because this class has not too many surprises. The assessments will be largely the same as the tutorials and the homeworks. So if you can master the tutorials, actually the tutorials are going to be a little bit more challenging than the assessments, because the tutorials you can do it at home, right? So the assessments you have to sit down here, so it will be a bit easier, the assessments. All right. So let us now do a quick recap on what we talked about last time. Recap on sets. Okay. So we have a certain universal set, and we're going to call this a sample space later on, universal set. And we're going to denote that by the Greek letter omega. So all the outcomes can only come from omega. So those are your head and your tail, and the 1, 2, 3, 4, 5, 6, and your roll or die. Okay. And we say that S is a subset of omega. Remember what this means? This is the same as for every, okay, maybe you don't know this symbol, but so for every element X inside S, X also belongs to omega. That means that S is a subset of omega. That is how we read it, okay? So now we recall also the notion of union, okay? So this is called union, just to put the English word here. All right, so this is the set of all elements X in the universe such that X belongs to S or X belongs to T. So the picture is as follows. We have the sets S and T, and this is the entire universe. And basically the union is this region here that contains both S and, S or T, okay? So that's the union, and you also have the intersection, okay, and that is denoted by this cup. Sorry, this is cap, right? In a latex writing, this is cup and this is cap, but doesn't really matter, okay? And this is the set of all elements within our universe for which X belongs to S, and that's the difference, X belongs to T. And so the picture is as follows. You're only concerned about the intersection. All right, and the intersection is this small little slice here. Okay, so you can easily check. One more thing is complement. We also talked about it last time. Complement, S complement is equal to omega take away S. And this is this symbol here, slash, all right, is read as take away or set difference. All right, and just to remind you, A take away B is equal to A intersect B complement. All right. So all the elements in A, but not in B. Okay. So that's the complement. All right. I think there's not much to say here, but here are some easily verified properties of the above operations, set operations. if I take the complement of the complement, so if I put bracket, I mean that we treat that set as an entity. Okay, so we treat this thing as one set. This is anyway a set. You take a complement of a set, you still get a set. Okay, and then we take complement one more time. What do you think we get? The set itself. Okay, right. So this actually can be proved, and there is a formal argument. Suppose I ask you to do this. What is the strategy? Last time I said that to show that two sets are equal, there's only one way of doing it. To show that two sets are equal, there's only one way of doing it, and the way is to show, okay, just as an aside, to show that two sets are equal, S equals to T, we show S is a subset of T and T is a subset of S. And to show, for example, that S is a subset of T, we take any element X inside T, S, and show that X also belongs to T. Okay, so that is the way to show that S is equal to T. All right, we need to show both sides, and to show one side, we have to show that X belongs, any X that belongs to S also belongs to T. Okay, so that is the way to do it. And I'll leave this as an exercise. So that's property 1. Property 2 and property 3 that I want to talk about look a little bit daunting, but they are not. Okay. So if I have two sets here, T and R, and I take their union, and I take their intersection with S. Now, what do you think this is? Well, this is S intersect T, bracket, union, S intersect R. If you read the book, they replace the R with U, but U looks too much like union, so I replace by R here. And the third property I want to talk about is S union T intersect R equals to S union T intersect S union R. Okay, so now all these things can be shown properly, but let me illustrate too with a picture. Okay, so here we have our universe, and we have three sets that are generic, so I will describe them as follows: S, T, and R. And on the left-hand side, you are looking at S intersect T union R. So T union R is this set here, and it is entirely this. Okay, so we do some coloring here. Okay, and how about S intersect this yellow part? Well, if S intersect this yellow part, you get this part, right? Right? So this is the left-hand side, and now let's draw the right-hand side and see whether they correspond. So I make a clean picture. So this is the left-hand side of 2. Now this is the right-hand side of 2, and see whether the orange region corresponds. Now the right-hand side involves S intersect T. So S intersect T is this green part here. You see? And then what does it also involve? Okay, it involves this S intersect R. S intersect R is this part here. All right, and now deliberately I will use this orange color, and the intersection of the green and the gray part, I apologize to people who are colorblind, is this part here, and it corresponds, and voila, we are correct. So that is a justification by picture, but you can justify this by mathematical arguments, by this purple argument here as well. Okay. So now I will pause to ask if anyone has any questions. So we have covered the notion of union and intersection. This is something that you definitely have to know. All right. And the third point there, exercise for the student. Okay. Does everyone understand the picture that I've just drawn? Is it clear? To illustrate point 2. Okay, very good. So there's a very systematic way of doing these things, as you can see how I do it systematically. Do union, do intersection systematically, draw the correct region. Okay? No, sorry. All right, any questions from the Zoom audience? So you will get some practice with this. You will certainly get some practice with this in the tutorial. Okay, to show some statements either through mathematical way of doing it or some picture Venn diagram way of doing it. So last time we also saw the Morgan's laws, which will be useful. Okay, it says the following. Suppose we have a sequence of events, sequence of sets, and all these are the subset of the sample space. All right. Then if you take the union of each one of them as run to infinity, take the complement, this is the same as you have to negate this and you have to negate this. All right. So that's the Morgan's laws. And there's another version as well. I'm not going to write that down. Okay. And here, last time at the end of the lecture, we actually showed this through proper mathematical reasoning. So this is just a recap. I'm just writing this down. Okay, so now I want to move on to probabilistic models, and we have not actually talked about probability. So now this is the first time we are doing it, and this is section 1.2 of the book, which you should read the whole thing. Okay, so where do we start? I've already alluded to this term several times, and that term is called the sample space. All right, def here is definition. This is a mathematical way of saying things. The sample space, which is always going to be denoted by omega, is the set of all possible outcomes of a random experiment. Okay, so for example, if you do fair coin tosses or even unfair coin tosses, then the omega is logically going to be heads and tails, heads or tails. If you do a dice roll, okay, these are very simple random experiments, then your outcome space or your sample space is a set of all integers from 1 to 6. Now, if you do, for example, two dice rolls, then your sample space is going to be 1, 2, all the way up to 6 times 1 all the way up to 6, the same thing. Now, this is something called the Cartesian product that I'm not sure whether people have come across or not, but it's just a set of all ordered pairs from 1 to 6. Let me write it in another way. So this is the set of all possible outcomes, say ij, that are ordered such that ij belong to the index set 1 to 6. So when you do two dice rolls, the order sometimes matters, all right? Because sometimes you might want to consider the difference between the two dice rolls. The difference, I minus j is not the same as j minus I, okay? But sometimes the order does not matter, in which case, for example, if you are interested in the sum of the dice rolls, you're playing Monopoly, you only care about the sum. Then you don't care about the order, but sometimes orders matter. And so, yeah, sample spaces, this leads me to my next point, in that sample spaces may be tricky to choose. And the book provides an example, may be very tricky to choose. And so here I have already illustrated that sometimes when you roll two dice, the order, the first dice, the second dice, the order matters. Okay, depending on what you are interested in. If someone tells you that I'm going to pay you the amount of money, which is the difference of the two dice, okay, then you might have to pay the person because the difference could be negative. I minus j could very well be negative. You might have to pay the person. All right, so a possible outcome space or sample space may be different from if someone says, oh, you roll two dice and you can move this number of moves on your Monopoly board, which is the sum of the two dice. All right, so the outcome space may be different. Just to exemplify this difference, let us look at the following two experiments. Example, receive $1 each time a head appears in 10 coin tosses and receive $0 otherwise. All right, so you toss a coin 10 times and then you receive $1 each time a head appears. So what would be an appropriate sample space? Okay. Now, because you only care about how many heads appears in the 10 coin tosses, right? So we only have to count the number of heads. So an appropriate sample space would be 0, 1, 2, all the way up to 10. This is an appropriate sample space for this particular experiment. Can you think about it? You're going to receive $1 each time a head appears. How many? What is the minimum number of head that appears? You could be super unlucky and no head appears, 0. Okay, so that corresponds to the left-hand side element of omega. Now you could be super lucky and you can get the maximum of $10 and you get the right-hand side of omega. Correct? So that is a very nice sample space. Very nice sample space that models this experiment. Okay. But again, now you toss a fair coin 10 times. And what happens here? Now this English is a bit long. You receive $1 for every coin toss up to and including first head, semicolon, then receive $2 up to and including second head, and the dollar amount that you receive doubles each time a head appears. Okay, I don't actually like all this long English. So let's illustrate this with an example. So suppose your coin tosses, the outcome space looks like this. So how much money do you receive altogether if you interpret this correctly? Oh, you receive $1 each time, including the first head. So you receive 1, 1, 1, 1. That's the amount of money that you receive here. Oh, now you saw a head. Okay, then you receive $2 until the next head appears. Okay, then you receive $4. And here we say up to and including. So that corresponds to this inclusive. Okay, then we receive $8 here. So the sum of all these numbers at the bottom is the total number of money, or total amount of money you receive. So this is a random experiment, and you receive a certain amount of money for each sequence of 10 tosses. Now, would it be good to consider this outcome space or this sample space as before, even though we are doing the same base experiment of tossing a coin 10 times? Would it be appropriate to use omega or no, because actually now the order of the heads tails matters. All right, so more appropriately for this example, more appropriate sample space would be the set of all length 10 strings of heads and tails. Now, this will take me too long to write down. There are a total of 1024 elements here. Okay, so one of them is tails, 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 dot, 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 up to tails. This is a length 10 string. Tails, 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 dot, 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 tails, heads, and so on and so forth. And there are 2 to the power of 10, which is 1024 elements here. Yeah? Complicated? No, this 2 to the 10 is nothing on a modern computer. We can do this very easily. Okay? Right, we are not asking you to actually use hand. Some more modern computers can do this fairly easily. Okay? So as you can see here, depending on what you're interested in, you may have to define the sample space in different ways. Okay? But usually, it is quite obvious what we should do. Okay, by the story. And usually, I would not ask you to define the sample space because it's just a very basic thing. The sample space will be typically given or very, very obvious. Okay, now we need to define the notion of a probability law, which is a little bit tricky. The probability law is defined on the sample space P assigned to each set A, which is a subset of omega, all right, called an event a non-negative number, PA, that encodes our belief about the collective likelihood of elements in A. Of elements in A. Okay, so the picture is as follows. There are too many words here. So you have a certain random experiment. Okay, and it generates a certain outcome here. So there's an outcome space. It generates a certain outcome. All right. And we are looking at, say, this subset here, A. Okay. And what does the probability law do? The probability law does the following. Okay. For this particular subset A, and there could be another subset B, it looks at the size of this particular subset, say this size here, and assigns it a certain number from 0 to 1. Okay. Now, there could be another event or subset of interest, say P. And then basically this is the action of the probability law, P. It brings this event B to another number from 0 to 1. Okay. So the probability law is basically, in mathematical terms, a function. Okay, a function that brings you from events in the probability space. This is omega. Okay, so omega contains many subsets. There's one subset there called A. There's one subset there called B. And basically the probability law is a certain mapping, all right, from subsets to numbers. Numbers between 0 and 1. Now, in that definition that I wrote down there, I didn't say between 0 and 1. I just said non-negative number, but it will turn out to be between 0 and 1, as we will discuss in the following. So this is a very abstract notion to you right now if you have not seen this flavor of introducing probability. But one more time, we have a certain random experiment that produces an outcome in the sample space. Suppose I toss a dice, all right? So the sample space here has 6 elements, all right? A here could be the set of even numbers, all right? So here could be even numbers, all right? So the probability law maps the set of even numbers to a certain number, all right? So if you have a dice with 6 sides, what's the chance that you get an even number? Maybe, if the dice is fair, 3/6, which is half. Okay, so it has this action here that brings you to 3/6. Now, suppose B is a subset of numbers less than equal to 2. Okay, which are the numbers less than equal to 2 in a dice roll? 1, 2. All right, so this is the set 1, 2. Then P here takes the subset and makes a number 2 out of 6. So these are some examples of this action. Now, I am now speaking in very abstract terms, but we will see in lectures and in tutorial more concrete examples. Okay, I also do not like all these abstract things. Okay, now this object here, the probability law, cannot be anything. Now, as you can imagine, right? Suppose A is a set of all even numbers, say 2, 4, 6. And B is a set of all numbers, say bigger than or equal to 2. So of course, B includes A, but not in this picture. We might expect the probability of the event B is bigger than or equal to the probability of event A. So the P here, the probability law, must satisfy some nice properties. Okay, so probability axioms that the sample space omega as well as the probability law must satisfy include the following. Number 1, for every event, the probability is non-negative. A subset omega. We call subsets of the sample space events. Okay, subsets of the sample space are called events. This is the sample space as usual. We always reserve omega for sample space. Okay, now if A and B are disjoint, okay, if A and B are disjoint, then what does disjoint mean? I.e., A intersect B is equal to the empty set. Then they have nothing in common. That's the meaning of disjoint. Maybe I haven't said it. I've not said that before, but now I'm saying it. Then PA union B is equal to, this is a very natural thing. Very natural. All right. You expect that the probability law is additive. This is called the additive property for disjoint events. Very, very natural. Okay, so these are some very natural things that we expect of a probability law. So now, generalizing this a little bit more, if A1, A2, A3 is a sequence, that means a collection of disjoint events, what does this mean? Okay, disjoint events means that if I take any two different indices, AI, AJ, then they give me the empty set. Okay, for all I not equal to J. So if A1 has nothing to do with A2, A3 has no intersection with A4, etc. Okay, then I take their union, okay, I running from 1 to infinity AI. So we have already defined what is this notation, is the infinite union from last time. Then this is nothing but P of A1 plus P of A2 plus P of A3 plus so on and so forth. Now these are called, these have names, and this is called the additivity for obvious reasons. And this is called countable additivity for obvious reasons. Countable additivity. You don't need to know these names, but it's just a good way to remember. So here is the picture here. You know, you have this sample space here, and you have two disjoint events, is A and B. So the probability of the union, this is the union. All right, the probability of the union, A union B, is nothing but the probability of A union, probability of A plus probability of B, and so on. And this can be extended to the countable cases, countably infinite case as well. Okay, all right, so this is another axiom. And the final one is probability of the full set is equal to 1. Now, these are three axioms, maybe 3.5, all right, because here you have, this is actually a consequence of this. These are three axioms that you have to commit to memory, okay? But these are very logical things that I won't take up too much of your brain power space. So you should commit them to memory. Now, remember, look at these axioms here. There's actually a lot of things I have not told you. For example, what is the probability of the empty set? Nowhere does this say that the probability of the empty set is whatever number. But it will be good for the probability of the empty set to be 0. But is it 0? Can we deduce that just by using these rules, nothing more, nothing less, you can tell me that the probability of empty set is 0? So this requires a careful argument, actually. So claim the probability of the empty set. Remember what's the empty set? It is the complement of the full set. Okay, claim the probability of the empty set is 0. Notice this is obvious. To an engineer, this is obvious. But to a math person, it's obvious, because what are we allowed to do at this point? We are only allowed to use our axioms. We are not allowed to use any other thing. We are only allowed to use the above 3 rules. If you use any other thing, violating the physics. So can we just use the above 3 rules to show this? This is logical thinking, okay? So let's show this justification. Now, from rule 3, from axiom 3, 1 is equal to the probability of omega. This is axiom 3. Maybe we make this axiom 3. Okay, we make this axiom 2. And we make this axiom 1. Okay, from axiom 3, we have this. Okay, every step is justified. If you forget about my class, right, it's okay. After you get out and you forget about me, it's okay. You forget about my class, you forget how to do properties, okay. But you cannot forget about how to think logically. If you eventually become an insurance agent, you also need to think in a logical manner. And this is what I'm inculcating here. Okay, anyway. So what is the next thing? You see, probability of omega is probability of omega union empty. If you take the union of the empty set to anything, you get the same thing. All right, this is something that I think we mentioned last time. All right, hopefully this doesn't restart, man. Okay, so this requires a moments of thought. If you take any set, you union it with empty thing, you get the same thing. Cool? We accept this. Now, what's so special about these two sets, omega and empty? They are, it starts with D. Disjoint. Yes, disjoint. There's nothing in common. All right. So this becomes, it can separate into this plus this. And here's the disjointness in which we use property 2. Right? So another application of property 1 or property 3, for example, is 1. This guy is equal to 1. This is property 3 plus probability of the empty set. Now, 1 minus 1 is indeed equal to 0, and this we can assert is 0. So you see everything here is logical. Okay? So we are not using any other thing. Okay, in fact, we didn't use property 1. We used property 2 and 3 here. Is that clear? All right, so there are a few things here to think about and to justify actually. This is a bit of abstract thinking, but when you come to university, you need to think abstractly. Okay, the first thing is, how do you get the second equality? All right, how do you get the second equality here? You need to think about it. And how do you assert the disjointness? What is the meaning of disjointness here? And in particular, omega intersect phi is equal to phi. Two sets are disjoint if their intersection has nothing. But since this set has nothing, so the intersection must have nothing. Okay, so here we are using disjointness of the two sets in order to apply property 2. Okay. Now, any questions from the audience? David says, yes, yeah, you can say that. Can you provide a proof by using the fact that the complement of the universe set is the empty set to show whatever we want to show? Just by using the axioms, we need to think a little bit. All right, you can give me a proof of that. Now, here is also another claim. Suppose we have A1, A2, all the way up to AN. Finitely many sets. Finitely many sets or events. Okay, now, hang on, finitely many, say, disjoint sets or events. Then the claim here is that if I take the union of AI, this is the meaning of this is A1 union A2 union ... union AN. This is equal to probability of A1 plus ... plus AN. Now, folks, this thing here, right, is not property 2. All right, property 2 says, if you go up, that if I take two sets that are disjoint, they sum up nicely like this. And property 2b says that if I take countably infinitely many sets, okay, sequence of disjoint events, countable infinite, then you have this sum here. But what I'm trying to ask here is, okay, I have more than 2, but not infinite. Then do I still have this very natural property? Just by using the above. Do you see the subtlety? We have not said that you can do more than 2, say 3, say n is 3. We have not said that you can do, we can write this down for n equals to 3. Do you see the subtlety here? Property 2 says that you can do it for 2 and you can do it for infinite. Can you do it for 3? How to do it for 3? There's one obvious way and one not so obvious way. Okay, say n equals to 3. If you can do 3, you can do 4. How to do 3? Let's see. Any brilliant suggestions? We are not so ambitious. We do 3, okay? So we are only interested in A1, A2, A3. They are subset of omega, and we are interested in the probability of this. These are disjoint. And we want to show that this is the sum of these 3 things. Probability A1, probability A2, probability A3, the sum of them. How? All right, first the easy thing to do is the following. A1, this is the same as A1 union A2 union A3 like this. You can put bracket around the last one. That means no matter how you take union, whether you take this one first or you take the last one first, same thing. This actually requires a moment of thought. Now, now you realize something. The union of 2 sets is indeed a set. So now you are left with only 2 sets here. One set and another set. Oh, beautiful. Now we can apply property 2 because we only have 2 sets. So we can split it up. Plus probability of A2 union A3. At this point, what do you have to ask yourself in order to apply property 2? The sets A1 and the union A2 union A3, they must be, it starts with D. Disjoint, right? But if A1, A2, A3 are disjoint, can you convince yourself that A1 and A2 union A3 are disjoint? You need to convince yourself about that. Okay? So this must be disjoint from this for us to be able to apply this, but this is true. You can draw a picture to verify. All right, so the picture is as follows. This is A1, A2, A3. And A2 union A3 is this part here. A1 is here. So clearly the A2 union A3, the orange part is disjoint from the yellow part, right? So let's make this yellow. So you have this decomposition because you're allowed to do 2. All right. Are you allowed to do one more time? Yeah, because now A2 is disjoint from A3. So you have the following very natural thing. Okay, very natural conclusion. But pardon? Any question? It is the, okay, this one here is the probability of the union of A1, A2, and A3 here. Okay, and what I'm trying to say here is that suppose I have finitely many disjoint events or sets, can I claim that the probability of the union is the sum of the probabilities? Okay, now I just wanted to do this example to mention that there's something non-trivial and subtle here. Because in property 2 here, we did this for 2 sets. You're allowed to do this for 2 sets. Okay, you're also allowed to do this for infinitely many sets. I didn't say that you're allowed to do this for 3 sets. So here, what I'm trying to say is that, okay, let's do 3 sets and let's use property 2 times to assert that we can actually have this decomposition for 3 sets. Now, if we can do this for 3 sets, we can do this for 4. Do you agree? What do we use? The same thing. We can use something called mathematical induction. Okay, that I'm not going to mention too much here. Is this clear? Is this clear? Oh, property 2 is here. So property 2 says the following: if you have 2 sets that are disjoint, then the probability of the union is the sum of the probabilities. Now, if you have infinitely many, okay, then the probability of the union is also the sum of the probabilities. Okay, but I didn't say that you can do this for 3. We just showed that you can do this for 3. homework for you to do it for 4, 5, 6, 7, 8, all finite. Okay, but it's believable, right? Yeah, I just use the same procedure. So the point I'm trying to make here is that there are many things we have not deduced, but these three properties are enough for us to do a lot of things. For example, to show that the empty set has probability 0. And for example, for us to show that the probability of the union of 3 disjoint sets is the sum of the individual probabilities. Okay? Is this absolutely clear? Yeah. 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 If it depends. Okay. If I say there, you should provide a formal justification without drawing picture, then you should follow the instruction. If I say that, oh, you can draw picture, then you can draw picture. Is that clear? Yeah. Usually, I will not ask this type of questions. I will ask calculation questions. So there will be minimal ambiguity about what you can do versus what you cannot do. Okay? Yeah. And I'm always a very reasonable person. Yeah. Yeah. I mean, we showed that, the axiom says you can assume that if there are 2 sets that are disjoint, you can add them up. If there are infinitely many sets that are disjoint, you can add them up. But these 2 axioms didn't say that if there are 3 sets that are disjoint, you can add them up. So there's something for us to do, which I just did for you. Now, then the next question is, if there are 7 sets that are disjoint, can you add them up? All right, that exercise. Okay. How what? Use the above axioms to show that. Yeah. That means you are only allowed to use the above axioms. Is that clear? Yeah. Okay. Right. I know this is a little bit abstract, but let us try to make things concrete. Okay. Example. Say we are dealing with coin tosses, so our sample space is very simple, 1 coin toss. And our sample space just consists of head tails. And so the set of events is a set of all subsets here. Events include, set of events include the empty set, the set just containing heads, the set just containing tails, and the set containing head and tails, which is equal to the full set omega. So these are the set of all subsets. And it is very natural if we are doing a fair coin toss to assign the probability heads to equal to probability tails, which is equal to half. Okay, and the probability law that is specified, a probability law takes each element, each event into a number. So it takes this into the number 0. It takes the probability of these into a number which is half. Okay. And finally, it takes the full set, which is equal to the probability of heads or tails into the number 1. So as you can see here, look at this picture again that I drew. For every event, you're going to produce a number. Here, for every event, and there are 4 events here, you produce a number. Here, you produce number 0, half, you produce a number half, and here you produce the number 1. That is what the action of the probability law does. Is that clear? Okay. Right. So now let me talk now about the discrete probability law. This is the easiest type of probability law. Okay. Discrete probability law, which is everything that we have been doing right now is discrete. Continuous we'll do later on. All right. Continuous is a bit tricky. So if omega, the sample space, consists of a finite number of outcomes, say S1, S2, dot, 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 Sn, the probability of any event, which is a subset, say S1, S2, up the way up to Sk, where k is less than equal to n bigger than 1. Okay, so you have all these outcomes, S1, S2, S3, all the way up to Sn, say S3, S2, S1. So these S's could be the faces of a die. Say n is 6 and k is equal to 3 here. So you're only interested in these outcomes, okay, out of all n. Then clearly the probability of this event S1 up to Sk is nothing but the sum of the individual probabilities S1 dot 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 up to Sk. You're just summing them up, okay? And now this is kind of obvious, all right? But can anyone tell me what I've done wrong? Something is amiss here. Something is not ideal. Something, if I write this in an exam and I'm not very lenient, sorry, if I'm a student and I write this in an exam and the professor is not very lenient, the professor would take away some marks from this sort of writing. What is wrong? Let's see whether the Zoom people. Oh, very good. Fu Fang Kang, very good. Has very good ears because he is listening. All right. So this notation here is fuzzy. Right? It is not good because whatever you put inside the probability law must be an event. S1 is not an event, but this should be written as S1 like this. But in the class, when we write probability S1, we really mean the probability of the event that consists of only one element, which is S1. So these two are synonymous. Synonymous means the same thing. Okay, and Fu Fang Kang, very perspicacious, very, how to say, alert. Okay, so that's the discrete probability law. A simpler thing to think about is the discrete uniform probability law. This is uniform. Okay, so if omega, the sample space, consists of n possible outcomes, which are all equally likely. Say a row of a dice, all the outcomes have probability 1/6. They're all equally likely. Then the probability of event A subset omega is probability of A equals to the number of elements in A divided by n. And we use this notation here to mean the number of elements in A. Okay, everything I talk about up to now is a little bit theoretical. So let us do an example of this discrete uniform probability law business. Okay, we will often illustrate concepts through examples. Here we roll two 4-sided dice. 2, all right? So all the faces are equally likely. This one I should say. Otherwise, you might think that the dice are biased. Roll 2 4-sided dice. So the outcome space or the sample space is a set of all ordered pairs ij such that I runs from, maybe we be a bit more formal, belongs to, I and j belong to 1, 2, 3, 4. So that's the sample space. Okay. And because these two dice are all fair, all outcomes, how many outcomes are there altogether? How many outcomes are there altogether? 4 times 4, which is 16. Yeah? Okay. So probability of every outcome ij is equal to 1/16 for all outcomes ij in omega. Okay? When I write this ij like this, I mean an ordered pair. Okay. So for example, the probability that you get 1, 1 is equal to 1 over 16. The probability that you get 2, 3 is also 1 over 16. And so on and so forth until the probability you get 4, 4 is also 1 over 16. Hopefully this is clear. Okay. Now, the rest of the questions are not so clear. All right. Needs some thinking. Even I also need to think. So we can represent this by means of a grid. Okay. By means of a grid here. So here we have the first dice, and here we have the second dice. Okay, and we label them as 1, 2, 3, 4, 1, 2, 3, 4, and we are interested in several interesting events. What is the probability that the first row is equal to the second row? So now we need to look at this. Now, basically here, this grid here is your entire sample space, right? You can draw it out. It's your entire sample space. I'm interested in the probability that the first row is equal to the second row. All these points here are equally likely in the sense that the chance that I hit on one of these points is 1 out of 16, as I've written down above. Now, where is the event that the first row is equal to the second row? It's here. This diagonal here. The first row is equal to the second row. How many dots are there? 4. So by using this formula here, number of outcomes that are successful, you divide by the total of outcomes, then this is how much? 4 out of 16. Clear? All right, so we are using the formula for this not so simple experiment. Any questions? Yeah, David, you can do it in that way also, I guess. Yeah. So how about, let's say, another exercise, okay? First row bigger than second row. Where is this present? Where is this? Here is a strict inequality. Yeah? Here, this makes a difference. Strict. Where are we now? Where are we present? You look at this grid here. I think we are here. This triangle here. Right? That is where the first dice row is bigger than the second dice row. You can go and check individually. Check one by one. All right, so in exactly this triangle here. Now, how many dots are there in the triangle, the green triangle? Yes, good. Perfect. Great audience participation. 6 out of 16. Okay. Now, all right, doesn't matter. Simplification, everyone can do. Now, let's do a final example, and then we take a 7-minute break. At least one row equals to 4. So at least one of the rows has the number 4. Now where are we? Where are we? We are here. Can you see? One of the rows is 4. At least one of the rows equal to 4. Which means you could have 2 rows equal to 4. That corner and the right-hand corner. Right? So in the purple region, if you track everything carefully, at least one of the rows turns out to be 4. Can you see? For example, this one here, the second row is 3, the first row is 4, so one of them. Here, actually, you're very lucky, 2 rows equal to 4. Okay, but now let me invite this gentleman here to tell me how many dots there are here.
7 dots.
Perfect. So we have 7 dots out of 16. So we have learned how to use the formula, right? Okay. So as promised, now we will take because this lecture is 2 hours. So let's take a 5-minute. Just now I said 7 minutes, right? So 7-minute break. We will start again at 3:01. Okay? Why do you keep saying the same thing? you know, if you keep saying the same thing, it becomes boring, you know. Can you have a bit of variation?
Let's go ahead for this.
What you're talking about is very unexciting. Not like what I'm talking about. Everything I'm saying is different. right? At least you tell me a story, right? That is more exciting. Okay, we come back at 3:01. At the tutorial, it exists, right? I want to mention that so I want to mention that it is really imperative for you to do the tutorial, or at least look through it, look at the questions in the book, because it's good practice for you to struggle through. The questions in the book are actually not so easy. By the way, this book is the book I used to learn probability last time, many years ago. What is woe? This is the second edition. Yeah. Okay, I want to mention that there exists office hours at 4 p.m. every Friday at my office. You can come and ask me any question. By the way, office hours is the American way of saying consultation hours. In NUS, you all call it consultation hours, I think, or whatever. All right. But you can come and ask me any question, right? Okay, so it's 3:01. Let us get started. All right, so just now we talked about discrete models. So the sample space only has finitely many objects, but you could conceive of many experiments for which the sample space is, for example, the interval 0, 1. So that, let me recall, is a set of all real numbers. That is a set of all real numbers such that x belongs to 0 to 1 inclusive. Okay, so you could conceive of an experiment such that the wheel is there's a certain wheel calibrated from 0 to 1. And when I spin it, I get a number uniform in the interval 0, 1. Okay, so I do not know how to draw this picture, so let me try my very best. So you have a certain wheel, and you are here, and you're looking at here, this point here, and so every location of the wheel is a certain number. Okay, it's a certain number, and then someone gives it a good hard spin, a very good hard spin, and then you observe this number here after the spin. All right, and there are infinitely many numbers here. Okay, for example, the strange number here, like 1 over pi. 1 over pi is a number between 0 and 1. Okay, and you could observe that. All right, so what is the chance that you observe the number, say 0.5? It's uniform. This is actually a very tough question. Very tough question that you require a few math courses to understand if you want to understand this properly. But suppose that the probability of seeing 0.5 is positive. Positive means bigger than 0. Now, because I said uniform, so the probability I see 0.5 is the same as the probability I see 0.25. So I can actually assign this a number, say A, bigger than 0. This is the same A, uniform, same. Suppose the probability of seeing 0.5 is a positive number A. Okay, it's the same for 0.25. But how many numbers are there here? There are infinitely many numbers here. So the point here is that there are infinitely many numbers in the interval 0, 1, which is omega. If I pick sufficiently many such numbers, the probability of that event, of picking all these numbers will exceed 1. Okay, so what I'm talking about is the following. Suppose I pick a certain number, say x1, x2, all the way up to say x capital N, for n large enough. All right. then this is the same by the fact that this set here, x1, x2, all the way up to xn is disjoint. You can partition it into this way, union, xn disjoint. And this can be added up, right? This can be added up, probability x1 plus probability x2. We are using one of the axioms, plus probability xn. And each one of them is a plus a plus a plus dot 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 plus a. All right. So here you have n of them, n of the a's, and a is a fixed quantity. If a is positive, I can choose n so large so that this is larger than 1. So the probability of individual numbers in this interval cannot be positive. Otherwise, we will overflow the probability budget of 1. So the probability of any number, say 0.5, must be equal to 0. Okay, so if I randomly generate a number from 0 to 1, actually the probability that I see any number, say 0.5, is 0. Okay, this is a little bit difficult for you to grasp. So it took me like several years. But this is true. And I do not want to spend too much time to explain why this is the case right now, because we will come across continuous random variables later on, in which we will have a more detailed discussion. But I just want to end with the note that it makes sense, in this case, to assign a probability of b minus a to any interval of length b minus a. Okay, so we have this. Okay, we have this interval from 0 to 1. Now, if we have a length, if we have a interval of, say, length, this length here is, say, 1/4, then it makes sense, and this is a, it makes sense to assign probability 1/4 to this interval. We cannot talk about individual elements. We can only talk about intervals. We can only talk about probability of intervals. That will give us a non-trivial positive number. If we talk about, say, just one number here, the probability of this one number, say 1/8, is exactly equal to 0. Okay, so that is what you have to keep in mind when we deal with continuous models or continuous random variables, but we'll deal with this later on. So this is a bit tricky. Okay, so now let me deal with this question. Yeah, this is because the probability of A is infinitesimally small till it tends to 0. Roughly speaking, that is the case. Yeah, but to formally talk about this, we need like 3 math courses. All right, so we don't have to worry too much about this at this point in time. Okay, any questions? Despite me telling you not to worry too much about this, I was actually deliberating whether to talk about this or not. Okay, yeah, so our sample space is in fact this space here. But we can only talk about certain special subsets of this sample space. If we talk about individual elements of the sample space, like this 1.18, then we get probability 0. But if we talk about some intervals that have non-zero length, like this interval with length 1/4, then it makes sense to assign probability 1/4 to it, of course. Okay. Right. So now let me, is there a name to this paradox? This is actually not a paradox. This is a, if you want a name to this paradox, you can go and Google measure zero events. Okay, you can Google this, okay? Probability 0 events if you wish. Yeah. Very interesting. If you want to talk about this, sometimes I teach this sort of things, but over in the math side. Okay, so other properties of the probability law of P, the probability law. Okay, now just now we talked about 3 properties, 3 axioms, and we also showed, for example, that the probability of the empty set is 0. Okay, so some other things that we could show include for all sets A, B, subset the sample space such that A is a subset of B, the probability of A is not more than the probability of B. Who says this is true? Later we will show that this is true. Okay. Now, B says the following. Probability of A union B is, now here we're not assuming A, B are disjoint. A plus the probability of B minus the probability of A intersect B. This one has a name. This one has a name. If you want to Google it, it's called the inclusion-exclusion principle. I don't think the book uses this name, but you can find this name. Okay, and see here, we will show some of these. See here says that the probability of A union B, not necessarily disjoint, is upper bounded by the probability of A plus the probability of B. So here are three things that are true, but can we show that they are true from the three axioms that I mentioned before the break? Justification. How do we think about such things? Justification of A. How do we justify this? First, before we do any justification, we have to believe it is true. So we have A here, it is nested inside B. It's a subset of B. That's the picture associated to this. Okay, so A is a subset of B. Then the probability of that subset A cannot exceed the probability of the subset B. How do we justify this? Now, you see, we start with probability of B. All right, B can be split up into two ways. It can be written as probability of A union the probability of B take away A. This is not so trivial. You see, this is A, it's this part here. But B take away A. B take away A is this part here, which is outside here, the outside part. Right, you see, you are splitting these things up nicely. Can you see? I split up the set B into two parts. And these two parts, the yellow part and the orange part, have a certain property. They are this. The yellow part and the orange part have a certain property that starts with D that is very useful. Do they have any intersection, the yellow part and the orange part? They are disjoint. Okay? So A and B take away A are disjoint. So by using property 2 on disjointness and additivity, I think I call that additivity of two sets. So one set is A and one set is B, take away A. By property 2, I can split this up into a nice sum. Cool? This because the two sets, as you mentioned, are disjoint. And property 2 says that, okay, if two sets are disjoint, the probability of the union is the sum of the probabilities, right? Now, cool. So now, what do? Property 1 says that all probabilities are non-negative. And we are done. Okay? Because all probabilities are non-negative, the probability of any set C is non-negative. So this guy here is bigger than or equal to 0. And we can drop it. We just have to include a bound here. So that's how we justify the first line here, the first claim here. That's how we justify this. Okay. Right. How do we justify the second one? All right. So what is the second line? This inclusion-exclusion principle. Okay. I'm not going to do this in full. We're just going to see how it is believable. All right, so this is our sample space. And this is the set A, this is the set B. Okay. Now, on the left-hand side, A union B is this set here. All right. And A itself, this set here, is this part here. And B itself is this part here. So if you add up the probability of A and the probability of B, you're adding up their intersection 2 times, right? This part in the middle is overlapped. This part in the middle has overlap. So you should, in order to just consider the union of A union B, you have to take away the intersection, one of them, one copy. Is that clear? Just from the picture, A, B, the intersection part is counted twice, right? It's counted twice because there's one layer here and one layer here. So you need to take away one of the layers, and that accounts for the last term minus PA intersect B. Okay, that's a way to think about things. And the last statement here, this has a name also. This is called the union bound. Now, the way we justify this union bound is to say, okay, we have the inclusion-exclusion principle, and all probabilities are non-negative. So here you're subtracting something, right? Here you're subtracting something. You're subtracting a non-positive number. So if you want to get rid of this, you will have an upper bound here, right? If you want to get rid of some positive number, say 0.1, this is say minus 0.1. You take it away, then this will be larger, this one larger, right? Agree? This is an inequality thing. Okay, Ken? So that is the way to justify the last line from the inclusion-exclusion principle. Any questions? Now, this is also easy to see from the picture. The union is this green part here. Now, if you add up the individual probabilities, you overlap this one. There's extra middle part, right? There's an extra middle part, so you have some extra probability. So this part here must be bigger than or equal to this part here. And the equality holds if and only if the sets are disjoint. Because if the sets are disjoint, A intersect B reduces to the empty set. And the probability of the empty set is 0. Okay? Any questions? This is a bit, unfortunately, we have to go through all this set theory and probability on basic probability before we can do some more exciting things. But we have to get all these formal things out of the way. Unfortunately. Any questions? Yes. Yes, here A and B are not necessarily disjoint. Yeah, but okay, so it's a special case. If A and B are disjoint, i.e. A intersect B is equal to 0. If empty set, this implies that probability of A intersect B is equal to 0, as we have shown. Then this guy here reduces to this guy here, but this goes away, so this reduces to just PA plus PB, which is axiom 2. Clear? Which is what you said. Any other questions from the audience? Any other questions from the Zoom people? Sorry, so to repeat, we minus because we have 2 value of this if we don't. Yeah, We only want one value of this, okay? So another way of seeing this, if you want the slow motion way, is the following. Remark, okay? This may confuse you more than necessary. A union B is what? A take away B. Union B take away A. Union B intersect A. And these are disjoint. Why? Because you have this A and B, and this is the middle part, the intersection. A take away B is what part? It's this part here. Okay, B take away A is what part? Is this part here. Right? And A take away B is what part? Is this part here. So now, as you can see, these three parts are disjoint. So probability of A union B is exactly an equality A take away B plus B take away A plus probability of B intersect A. Okay, you can also write this in an exact way like this. Okay, you can also write it in an exact way. All right, but now here, instead of this minus, this becomes a plus. So how do you resolve that these two expressions are the same? That requires some effort. Okay, but you can see that there's only one part here. There's only one part here, and that is manifested here. Now I've split the unit into three disjoint parts. Okay. Yeah. So this is another representation for the union in which you see the three parts very carefully. Okay, but the best way to look at it here is to look at the fact that this part here is repeated twice. So we need to take away one copy if they are not disjoint. Clear? Okay. Okay, so the last thing I want to talk about today, I just want to start on this. All right, this is not a very easy concept, but I want to talk about conditional probability. Okay, by the way, before I talk about this, right? Exercise for the student. Show that this reduces to the what I call inclusion exclusion equality above. Okay, exercise show that this reduces to that inclusion exclusion equality, which is here. This line here. Show this. It doesn't look the same, no, but somehow can you massage it so that it looks the same? Okay. Oh. Okay. So now I want to talk about the last thing that we want to talk about today, which is conditional probability. Now, oftentimes, right, you have some additional information. Suppose I have some coffee in the morning. I am going to be more alert. Suppose I study very hard. Then I will not end up in your situation where you keep thinking that you are not going to do well. So we have additional information, all right, about some situation. So, okay, give you an example. If you know that the sum of two rows of a dice equals to 9, what's the probability that the first row equals to 6? All right, so you already know that you toss two dice, the sum is 9. Okay, what's the chance that the probability that the first row is equal to 6? Okay, so this is some information, right, that someone has given to you. Now, if maybe simpler question. This question is from the book. I don't like this. Now, if the sum, can someone tell me straight away? I change it to 7. If the sum of two rows of a die is equal to 7, what's the chance that the first row is 6? Just use logic. 1 over Okay, we have one candidate answer there. Now, if you do not know this, okay, if you do not know that the sum of two rows of dice is equal to 7, what's the chance that the first row is 6? If you do not know that the sum is 7, that means you have no knowledge whatsoever. Then the probability that the first row of the dice is 6, right? It must be 1/6 because you have no additional information. But if you know that the sum of the two rows of the dice is equal to 7, what's the chance that the first row is 6? You see, if you know this, we have one candidate answer. If you know that the sum is this, what are the possible outcomes? It's only 1, 6 and 6, 1. Right? You cannot have what's the probability that the first row is 6? No. So here you can also have 2, 5 and 3, 4 and so on and so forth, right? So this is not so simple. Sorry. 2, 5, 5, 5, 2 and so on and so forth. So okay. So maybe not be so easy to figure out, but maybe it's 1, 6. Let's try to figure out later on. I was thinking too naively. Okay, but this is some additional information. All right, so we can try to figure this out later. All right, so this is some additional information that we want to use to improve our estimation of the probability of the first row. For example, if your COVID test is negative, what's the probability that you are COVID positive? All right, if it's negative, what's the probability that you're COVID? So this is some additional information. If you didn't have this information, you didn't do the test at all, what's the probability that you're COVID positive? It's going to be different from if you have this additional information, right? So conditional probability makes this precise. Okay. So now we are going to talk about definition of the conditional probability of an event A given another event B. Here A and B are subsets of the sample space omega. And this is denoted as probability A given B. This slash here is read as given because we are given this knowledge. So for example, let us consider the one dice row. Okay. Now you know that the outcome, someone looked at the outcome, picked at it, and told you that the outcome is even. Okay. What is the chance that the outcome is equal to 6? What do you think is a good number or logical thing to put here? Now, someone told you that the outcome is even. Even means can divide by 2. All right. So if the outcome is even, the only outcomes that are possible are 2, 4, 6, right? So basically, initially, before we threw the dice, we know that there are 6 possible outcomes: 1, 2, 3, 4, 5, 6. But someone already picked at it. Yeah, 1, 6 is correct. So this guy here listed all the outcomes such that the sum is equal to 7, and the chance that the first dice is equal to 6 is 1 out of 6 there. So your answer is correct. Okay, so let me now do this question here. This is very simple. All right, if the outcome is even, you know someone took a peek at it and he or she, okay, observed that the outcome is even. What's the chance that the outcome is 6? Logically, this should be 1/3 because it's 1 out of 3, right? 1 out of 3 chances, right? So it makes sense for us to talk about conditional probability, at least for the simple case of discrete sample spaces. Discrete sample spaces in which all elements are equally likely. Okay, all elements are equally likely. We're going to define this conditional probability. This equal with a triangle thing up there means defined, but if this looks very scary, never mind. Okay, is the number of elements in A intersect B divided by the number of elements in B itself. So that's exactly what I'm doing here. All right. This is number of elements in A intersect B is 1. Total number of elements in total is 3. Okay. So as you can see here in this particular example, number of elements in B, here there are 3, and I put 3 here. And the number of elements in the intersection is exactly 1, so that comes 1 here. So the intersection of this and this, only one element, which is 6. Clear? Any questions? Yeah, here, this guy listed down here. Should we be looking at the it affects. Suppose I do change this. I don't like 7, 12. Then does this change your belief as to what the probability that the first row is equal to 6 is? You look at the question mark. If the sum of 2 rows of a dice equal to 12, what is the chance that the first row is 6? No, row, record the number. Pick up the dice again, roll again, record the number. And then you record the sum. You throw the dice 2 times. And then you see that, oh, you can move 12 steps. 6, 6. There's only one outcome here, right? So what's the probability that the first row is 6? It is 1, right? So the answer is different from this guy listing down, and then your answer is 1, 6. So the number there equals to 12 or equal to 7 actually makes a big difference. Right? So we have to study this properly. It's what? Yeah, you need to understand a little bit of English here. So if the sum of 2 rows of a dice, actually I copied this from the book. If the sum of 2 rows of a dice equals to 12, that means you roll the same dice 2 times. And then you record the first row, you record the second row, but now you cannot record the individual rows. You can only record the sum. The sum, you notice that it's 12. Surely it must be 6, 6, right? There's no other choice. So the probability that the first row equals to 6 is 1. So this question here depends on what is this number, right? As you saw, if I change this to some other number, you get some different answer. Okay, right. So let's call this just S. All right. What is the sum? You can change S to any number, and then you get a variety of answers for this question. Okay. So now here is the important point here for this formula is that all elements are equally likely. But we don't have to have all elements are equally likely. Generally, we have the following formula. Probability of A given B, this is the conditional probability, is probability of A intersect B divided by probability of B. This is a formula that I want to warn everybody that you have to commit to memory. There's no need for Googling. You need to commit this to memory. Okay, and this is contingent on the fact that probability of B is positive. Now, in mathematics, you cannot divide by 0. All right, anything divided by 0 is illegal. So here we have to specify probability of B bigger than 0. If probability of B is equal to 0, can we define this? The answer at this class is no. The answer in some other classes is very much yes. Because in real life, we need to condition on some events with probability 0. But we won't talk about that here. It's a bit too advanced. Okay, so here, this is a formula that one has to commit to memory. All right, and this formula here generalizes the formula up there. Why? Note that in the special case that all elements are equally likely, what we have by the discussion we had before the break, this is equal to the number of elements in A intersect B divided by n, there are n elements, and probability of B is equal to number of elements in B divided by n, and so probability of A intersect B over probability of B is equal to the number of elements of A intersect B over n, you take this one, divided by number of elements in B divided by n. And if you have this, you can cancel the n here, and you recover exactly number of elements in A intersect B divided by number of elements in B, which corresponds to this formula. Yeah. So in the special case that all elements are equally likely, this formula reduces to this formula. Okay. Any questions? No questions from the Zoom. Any questions? So just a few remarks here, okay? For a fixed event that we are conditioning on B, conditioning on this event, right? Then P of A given B specifies a valid probability law. What does this mean? Now, what is the meaning of a valid probability law? We recall the discussion we had just now that a valid probability law must, for example, be non-negative, all right? Must have this property that the probability of the entire space is 1. Okay, and must have these additivity properties. These are 3 important probability laws. Okay, but now when we condition on a fixed event B, okay, and we look at this probability, this also specifies a valid probability law. Let us look at axiom 3. Does it satisfy? So let's assign A to be omega. Then we have to question whether this is 1. Is this 1? Because it has to be. So B is fixed. All right. So basically we have this sample space here originally, and we have this subset B here. That is a subset of the sample space. Instead of working in omega, now we are restricting all our attention. We are only looking at everything that's happening inside B. Nothing outside B can happen because someone already told us that the outcome lies in B. That means that we are conditioning on B. Is it true the third rule still holds? Is it true that the third rule holds? The third axiom. So let's check. All right. Probability of omega given B is equal to probability of the entire sample space intersect B divided by probability of B. Right? This is the rule from above. You just instantiate A to be omega. Okay, this rule, you instantiate. That means you take A to be omega here. Okay. All right, what is omega intersect B? Oh, you look at this picture. Omega intersect B, which is this part here. Well, oh, it's exactly this because B is inside omega. So this is B, probability of B divided by probability of P. Right? Because omega intersect B is B itself. Then, what allows us to say that this is equal to 1? Why is probability of B divided by probability of B equal to 1? What allows us to say that it's equal to 1? Yes. In mathematics, we cannot have 0 over 0. But I already said that everything that we are dealing with, the denominator is positive. So you are allowed to cancel. Okay? So because here is because probability of B is not 0 and particular positive. So the third axiom holds true. Exercise for you guys. Maybe I do one more. Okay, I do the finite additivity one, but the rest you do. Okay, so this implies that the third axiom holds. Now let's check the second axiom. But before I do that, are there any questions about this calculation? You know why the intersection of omega and B is B? You look at the picture. Intersection means common part. Huh? So the third axiom holds. So let's check that the second axiom holds. We are not going to check the first one holds. So what does the second axiom say? Okay, if I take, we want to now check that the second axiom holds. And what does it say? It says we have to check the probability of A1 union A2 given B. That means for all A1 disjoint A2. So if A1 is disjoint A2 and we have this, then we should have this question mark. This is what we should have. This is what is the second axiom. Finite additivity. It's called finite additivity. Okay, or pairwise additivity, whatever. So this is something we have to check. So let's check. Okay, where do we start? Left-hand side, which is this guy here. So the left-hand side is this guy here. And we just follow the definition, all right? The definition says, oh, okay, A1 union A2 intersect B divided by PB, right? This is the definition. Now you are taking this as your big A, okay, big A here. And then you need to intersect this thing here, this thing, and keep this. This is the definition. At this point in time, you note that A1 union A2 intersect B. I already said this at the beginning. Is A1 intersect B bracket with A2, this is intersect B union A2 intersect B. There's a formula over PB. Okay, I already illustrated this at the beginning. For three arbitrary sets, A1 union A2 intersect B, you can split it into these parts. Okay, you can split into this part and this part. And I'm not going to illustrate this again unless you really want me to. How to do this? If you really want me to, you draw pictures. Okay, so here is A1, A2, and B. And you have A1 union A2 intersect B, which is this particular region. Okay, this particular region. And you can see you can interpret it in a couple of ways. Okay, right. So I'm not going to belabor this point. Okay, but sorry, this picture is not very good. So the A1 and A2 are in fact disjoint. Okay, they are disjoint. So I should draw them as disjoint. A2. Otherwise, it doesn't work. Okay, so A1 union A2 intersect B is exactly these two parts of the region. This blue part. Okay, but you see that the blue parts themselves are disjoint. Okay, the blue parts themselves are disjoint. So this one can be split up into A1 intersect B plus A2 intersect B divided by PB. But this is equal to A1 intersect B divided by PB plus P of A2 intersect B divided by PB. But now we follow the rule, which is A1 intersect B plus probability A2 intersect B. So we see we have confirmed the finite additivity property for disjoint sets A1, A2. Where? So let me go through this one more time. So from here to here, it's just the definition of conditioning. You need to put B, you need to intersect B with this orange set. This divided by B is carried throughout, carried all the way. Until this point, you look at this expression here and you take this as your A and you apply the formula once again. This is the same as this. This is the formula. A given B is A intersect B divided by PB. Okay, got it. Yeah. So here we have verified axiom 2. Okay, we have verified this equality here. Cool. Now this is a little bit heavy, but at the university level, we need to use our brains to think. All right. As always, we need to use our brains to think. That's the purpose of our existence. Okay, now that's cool. Oh, David says it's cool. I also think it's cool. I do probability for a living. All right, so now let's end off this with an example to make everything concrete. Example, we toss a fair coin 3 times. So the sample space is basically heads, there are heads, tails, and there are 8 things altogether. So the number of elements in the sample space is 8. Hopefully you understand that. I don't have to mention. So this is the entire sample space. Okay. Let A and B be these events. A is the event. More heads than tails come up. And B is the event. First toss is a head. Okay. Now, how do we do this? So suppose we are interested, I ask you to compute this using the formula. How do you compute this? So now let's list down B first. What are the possibilities of B? First toss is a head. Heads, 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 tails, heads, tails, heads, heads, tails, tails. These are the only possibilities, right? For B. The first toss can either be tails or heads. I've listed down those outcomes that are heads only. A leh? How about A? First, more heads than tails come up. Okay, more. More means strictly more, cannot be equal. So more heads than tails. So heads, tails, 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 heads, tails. More heads than tails. No. More heads than tails. So heads, 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 3 heads here. Heads, heads, tails, and heads, tail, head, head, tail, heads, tails, tail, heads, heads. Any more? More heads than tails. Okay, correct. First toss is a head. Okay, so you see, these are the outcomes, right? How about A intersect B? Okay, what is the common part? What? Yes, A, very good. This is common. This one, common. There's one more common one, right? This one common. But the last one is not common. The order matters, okay? So the common part is this one. Right? Okay. All right. So when I ask you to compute this, not so difficult. Probability of A given B is probability of A intersect B. Just use the formula. Probability of B. What is probability of A intersect B? Well, 3 out of 8. Agree? That's the top. Because there are only 3 outcomes in the intersection. See, there are only 3. 1, 2, 3. And each one of the outcomes has probability 1 over 8. Because there are a total of 8 elements in the sample space and everything is the same, is the uniform. Agree? And then the bottom is PB, which is 4 over 8. Right? Agree? Everyone can follow my number? A intersect B is 3. Yeah, correct. So this is 3 over 4, which is 0.75, as what David said. Okay. Everyone can follow this calculation? Yeah, it's just listing, being systematic, but later on we'll do something more exciting. Okay. Next Monday is Tuesday. Yeah, Monday or Tuesday. We will continue our discussion on conditioning. All right. And we'll start off by reminding ourselves the conditioning the conditioning equality here, the thing I said you need to commit to memory. Commit to memory means memorize. Okay, commit this to memory. We will use this one more time to do another more involved example. But for now, you go home and you can convince yourself that this example is good enough for your understanding of everything. Okay, this example is good. Okay, to illustrate what is B, what is the story of B, what is the story of A, find out what is their intersection. Okay, and plug. Okay, so here PB is 4/8 because there are 4 outcomes. PA is also 4/8. PA intersect B is 3/8. And then we plug it in. And then we are done. Okay? Ken? Any questions? Pardon? No, A intersect B is very different from A given B. You see, A given B is this thing. A intersect B is only the on top. You need to divide by PB. Major difference. Okay? So here A intersect B is this part here. This is A intersect B. It is very, very, very different from A given B. Because you are missing this thing here. This thing here needs to be accounted for. So as I said, you commit this formula to where? Memory. Okay, there are very few things in life you have to commit to memory. But this one you need to commit to memory. Okay? Very few things in life you need to remember. I will post these handwritten things, handwritten notes. Hopefully you can read my handwriting. I write, my handwriting for English is terrible, but for math it's still readable. Hopefully. Okay, I will see you next Tuesday or Monday. I cannot remember. But enjoy your weekend. And we have what? What do we have tomorrow? Tomorrow is Friday. What do we have? Office hours. In case you have any questions, okay? But on Thursdays like today, right? You can come down to ask me questions. On the Tuesday lecture, it's a bit difficult because I need to rush off. Yeah. Thank you. See you. Bye-bye. Bye.